Hello, welcome. In this section, we continue our quest for solutions of first-order linear ordinary differential equations. Recall that the most general form of a first-order linear ordinary differential equation can be written as the equation shown in 4.2.1. A sub 1 of x times y prime plus a sub 0 of x times y equals g of x, where a sub 1, a sub 0, and g are some known functions of x. For example, the following equations are linear. In the first equation, a sub 1 is 1, a sub 0 is negative 1, and g of x is simply x. Similarly, in the second equation, a sub 1 of x is 1, a sub 0 of x is negative 1 over x, the coefficient of y, and g of x is x times sine of x. Observe that these equations are linear, but not separable. The following equations are not linear. Because these equations do not have the form as shown in equation 4.2.1, namely due to the y squared terms. If a sub 1 of x is not equal to 0 for all x in some interval I, then by dividing the both sides of equation 4.2.1 by a sub 1 of x, we obtain an equation of the form as shown in 4.2.2, namely y prime plus p of x times y equals f of x, where p of x equals a sub 0 of x over a sub 1 of x, and f of x equals g of x over a sub 1 of x. Equation 4.2.2 here is called the standard form of a first-order linear ordinary differential equation. To solve the equation 4.2.1, it is often useful to write it in its standard form, the form as shown in the equation 4.2.2. However, it is not necessary. Method of solution. In some cases, it is possible to solve a first-order linear differential equation immediately by integrating the equation, as in the following example. Consider the following first-order linear ordinary differential equation, where we identify that a sub 1 of x is the term 1 plus x squared, and a sub 0 of x is 2x, and the right hand side is simply g of x. The left hand side of the equation can simply be put into the following form. The derivative of the product of 1 plus x squared and y with respect to x equals 4x. when we differentiate the left-hand side with respect to x, we obtain the terms in the left-hand side of the given equation. Please verify. Now, integrating both sides with respect to x, we obtain the quantity 1 plus x squared times y in the left-hand side and the integral of the quantity 4x in the right-hand side. The right-hand side gives 2x squared plus c, where c is an arbitrary constant of integration. Now dividing both sides by the quantity 1 plus x squared and solving for y, we find that y equals 2x squared over 1 plus x squared plus c over 1 plus x squared. And this is the general solution of the given equation. Unfortunately, most first-order linear ordinary differential equations cannot be solved as illustrated in the previous example because their left-hand sides are not the derivative of the product of y and some other function. However, Gottfried Wilhelm von Leibniz, the German mathematician who independently co-discovered calculus, discovered that if the differential equation is multiplied by a certain function mu, then the equation can be converted into one that is immediately integrable by using the product rule for derivatives, just as in example 4.2.1. The function mu is called an integrating factor. And our main task in this section is to determine how to find it for a given equation. We will show how this method works first for an example, and then for the general first-order linear differential equation in the standard form. Consider the following example. We want to solve the first-order linear differential equation with the help of this integrating factor. First, observe that the left-hand side of this equation cannot be put as a derivative of some function. Let's try the method discovered by Leibniz. We first multiply the given equation through the quantity e to the negative x as given. Now, the left-hand side of this resulting equation can be put as a derivative of the quantity e to the negative x times y. Please verify. And the right-hand side simply becomes 1. Now, integrating both sides with respect to x, we obtain the following equation. The left-hand side is e to the negative x times y, and the right-hand side, when integrated, gives x plus c, where c is an arbitrary constant of integration. Now, solving for y, we get the equation in the box. And this is the general solution of the given equation. Now, we return to the general first-order linear differential equation, 4.2.2, namely y prime plus p of x times y equals f of x. Let's assume for the moment that mu of x is not equal to 0 for all x in some interval I. Then multiplying both sides by mu of x, we obtain this equation as shown in 4.2.3. Now also suppose for the moment that mu is a function of x such that its derivative mu prime equals mu of x times p of x. Equation 4.2.4. Then with the assumption 4.2.4, the left hand side of the equation 4.2.3 can be written as whereas the right hand side stays the same, which when integrated gives mu of x times y in the left hand side, and the integral of the product mu and f plus c. As previous, c is the constant of integration. And solving for y with the hypothesis that mu of x is not equal to 0 for all x in some interval I, we find that the equation shown in 4.2.5. This shows that the equation 4.2.2 can be solved once we know the quantity mu of x. To know that, let's get back to the equation 4.2.4, which can be written in this form. Mu prime over mu equals the function p. Integrating both sides, we obtain the natural log of the absolute value of mu of x equals the integral of the function p plus k, where k is an arbitrary constant of integration. By exponentiating both sides, we find the absolute value of mu of x equals e to the k times exponential of the integral of p, where we have applied the formula, the e to the natural log of the quantity a equals a in the left hand side. Now removing the absolute value bars from the left hand side of the previous equation, we get mu of x in the left hand side equals plus or minus e to the k times exponential of the integral of p. This shows that for any value of k and the sign, mu of x works as an integrating factor. Let's pick the simplest possible function, which can be obtained by setting k equals 0. In doing that, the term e to the k would simply become e to the 0 or simply 1. And choosing the positive sign in the right hand side of this previous equation. Then we get the equation shown in the box. Mu of x equals exponential of the integral of p. 4.2.6. This equation is the definition of the integrating factor of equation 4.2.2. Similarly, the integrating factor of the equation 4.2.1 is given by the equation shown in the box, 4.2.7. In the previous example, 4.2.2, we were given the integrating factor mu of this equation. Now we want to calculate this integrating factor out of this equation. By definition, the integrating factor mu of x equals exponential of the integral of p. In this equation, we identify that p of x equals -1 and f of x equals e to the x. The integrating factor only requires the function p. And then the integration gives us the following integrating factor, as we were given in example 4.2.2. Now recall that the first order linear ordinary differential equation in standard form has the solution as shown in the equation 4.2.5. We do not need to memorize this formula. Instead, we follow the following procedure each time. 1. Remember to put a linear equation into the standard form. From this standard form, identify the function p and then calculate the integrating factor mu of x. By the definition, mu of x equals the exponential of the integral of the function p. No arbitrary constant need to be put in mu of x while calculating the integral of p, as discussed earlier. 3. Multiply both sides of the equation in standard form by this integrating factor. The left-hand side of the resulting equation can always be written in this form. The derivative of mu times y with respect to x equals mu times the function f. Step 4. Integrate both sides of the last equation with respect to x and solve for y. Now we apply these steps to solve this example. We need to solve this initial value problem. The ordinary differential equation we see here is a first order linear differential equation written in its general form. Let's have a look at dissolution. Let's assume that x is not equal to 0. Then either x is smaller than 0 or x is larger than 0. But the initial condition here indicates that the interval has to be x larger than 0, since the initial point has coordinates 1, 2. X is here positive. Now rewriting the given equation in standard form by dividing by x, we obtain the equation shown in 4.2.4.1, where p of x equals 2 over x and f of x equals 4x. The integrating factor of the equation 4.2.4.1 is given by the definition of integrating factor. Mu of x equals exponential of the integral of the function p, which when integrated gives the exponential of 2 times the natural log of absolute value of x. Since we considered x is positive, and applying that here, we obtain the exponential of 2 times the natural log of x only, which can also be written as e to the natural log of x squared, and this simplifies to x squared only. So the integrating factor of our problem 4.2.4.1 is x squared. Now multiplying both sides of equation 4.2.4.1 by the integrating factor x squared, we obtain the following equation, which can be put into the following form. Now, integrating both sides and then dividing by x squared, we finally find the general solution of the given differential equation. To determine C, we can use the initial condition, y at 1 equals 2. So if we substitute x equals 1 and y equals 2 into the equation, we obtain the C value 1. Therefore, the solution to the initial value problem is given by the equation shown in the box for the interval x larger than 0. Now let's try to plot the solution curves of the equation we just solved. The solution was y equals x squared plus c over x squared. This is the general solution to the given differential equation. And this gives some members of this family. Corresponding to each value of c, we see some members of this family of solution. However, either the left-hand side of the y-axis or the right-hand side of the y-axis is a solution of the differential equation, since the solution must be defined on an interval, except the case c equals 0, where we get a parabola. This particular solution is defined on the entire x-axis. Now, in this figure, we superimpose some members of this family of solutions. Now we want to find one solution of this family that passes through the point 1, 2, the initial condition. And we see that the red curve shown here is the solution to the given initial value problem.